The Dark Energy Spectroscopic Instrument's second data release recently reported a 2.8 to 4.2 sigma preference for dynamical dark energy. To understand this anomaly, we must define lambda. Standard dark energy is static. Its equation of state, W, is exactly -1. But DESI's data shows the curve dipping down, reaching a W around -0.75, and crossing the threshold at redshift 0.5. In physics, this is called a phantom crossing. Under the strict rules of minimally coupled, single-field dark energy, this is mathematically forbidden. The universe cannot physically behave this way. Theorists typically rely on extreme structural additions to force a crossing. They introduce multiple interacting fields, non-canonical dynamics, or entirely modified theories of gravity. The cosmology community is left weighing two options. Either the standard model of the universe is broken, or the mathematical templates used to interpret this data are producing a false signal. In statistical analysis, there is a known vulnerability called template bias. When we analyze cosmic data, we feed it through standard mathematical fitting templates. These templates are rigid. If the true shape of the universe doesn't align with the template's internal geometry, the algorithm will distort the data to force a fit. A recent paper by independent researcher B. Shadow investigates this specific vulnerability by constructing a bounded clock mathematical model called Lcos. The paper tests a very precise hypothesis. It argues that an expansion history with entirely normal, non-phantom dark energy can mathematically hallucinate a phantom crossing when analyzed through our current industry-standard templates. Lcos is designed as an analytical diagnostic tool. It is meant to expose the mechanical flaws in our modeling, not to serve as a replacement for general relativity. Before we abandon the foundational laws of physics, we have to rule out the possibility that the DESI anomaly is simply a byproduct of a restricted mathematical lens. The standard tool for measuring cosmic expansion is the Chevalier-Polarsky-Rinder parameterization, usually called CPL. It relies on two specific parameters, W0, which defines the current equation of state, and WA, which dictates its evolution over time. CPL is essentially a two-parameter Taylor expansion. It works well for standard cosmological models, but its algebraic structure is tightly constrained. The problem arises if the universe's true expansion history contains a mathematical term that falls completely outside the CPL functional family. When a Bayesian fitting algorithm encounters a shape it cannot naturally trace, it still has to minimize the statistical error. To do that, it aggressively stretches its two available parameters to absorb any geometric mismatch. If we force the CPL template over a curve it cannot accommodate, the resulting parameters will artificially dip below the W equals -1 boundary, purely to satisfy the algorithm's mathematical constraints. To test this, Shadow builds the Lcos model by adjusting the standard cosmological framework. Normally, the expansion history relies on four standard density scalings: radiation, matter, curvature, and the cosmological constant. Lcos introduces a one-parameter deformation to this structure. It alters the expansion rate using a bounded clock non-vacuum kernel, governed entirely by a single parameter called S0. This mathematical deformation produces a highly specific output. It injects a -1 plus c to the power 1 term directly into the Hubble rate. This term is an algebraic residual created by the specific parameterization. It is not an independent physical fluid or a new form of matter. The paper provides a strict analytical proof for this model. Under the standard fiducial matter split, the lambda CDS structure guarantees that its effective equation of state remains strictly greater than -1 for all redshifts greater than or equal to 0. This yields exactly what researchers need to test the hallucination hypothesis, a mathematically guaranteed non-phantom universe to serve as a clean control environment. With the control model established, the paper runs a mock experiment. It generates a set of noise-free baryon acoustic oscillation distances based perfectly on the lambda CDS model, and then applies standard templates to see what happens. This chart plots the effective equation of state over redshift. The solid blue line represents the exact lambda CDS model. Notice that it remains safely above the dotted horizontal line representing the phantom threshold. But when the standard CPL template is forced to fit this exact same data, the orange dashed line emerges. It distinctly drops below the -1 threshold at low redshift. The problem isn't isolated to CPL. When the Barboza, Alcanis, and JBP templates are applied to the same mock data, the green and red dashed lines plunge even deeper into phantom territory. We are watching template bias occur in real time. These rigid two-parameter templates are actively pushing the W0 value below -1, strictly to absorb the curvature of that -1 plus z to the 1 term. As a final proof, the data is fitted with a more flexible three-parameter polynomial. The purple dashed line correctly tracks the true blue curve without ever crossing the threshold. The phantom crossing is a basis restriction artifact. It is a statistical mirage generated by inflexible mathematical tools. The theoretical proof holds up, but for Lcos to fully explain the DESI anomaly, it must survive the actual observational constraints from Joint Pantheon Plus and DESI Data Release 2 measurements. This plot maps the recovered CPL parameters against the underlying Lcos variable. Real-world supernova and BAO data cap this parameter at 0.19. At this strict limit, the maximum distortion the template can hallucinate produces a W0 value of -1.02. The actual DESI best fit finding reported a W0 value of roughly -0.75. The magnitude of the real signal is nearly 10 times larger than the distortion Lcos can generate. The mechanism of template bias is proven, but a gap in amplitude remains. The physical data restricts the Lcos model from generating a large enough mirage to single-handedly explain the massive DESI signal. The model does not erase the DESI anomaly entirely. Instead, it serves as a critical warning light, exposing the extreme fragility of the templates we rely on. The combined observational datasets still strongly favor some kind of geometric departure from the standard cosmological baseline. However, we should be cautious before immediately inventing exotic multi-field interactions or breaking general relativity to account for it. The cosmology community must rigorously test its mathematical parameterizations. We have to ensure we are not taking a smooth background geometry and forcing it to project a dynamical phantom crossing. Confirming or falsifying models like Lambda CDM requires distinct, observable criteria. Next-generation surveys like Euclid DR2 and the full survey DEFI release will need to deliver sub-percent precision on their per-bin measurements. That level of extreme observational precision is the only way to isolate the subtle -1 plus z to the first signature in the expansion history that separates standard models from these bounded deformations. The ultimate shape of the universe may not contain phantom dark energy at all. It may simply possess a subtle geometry that our current mathematical boxes haven't yet learned how to hold.